Okay, so we're going to look at some Fisher projections of monosaccharides. So in order to do this, we're just going to look at our three most common monosaccharides and what they look like. So I went ahead and drew out kind of a backbone for you guys for each of these starting out. So first off, we're going to talk about glucose. So it's the most common monosaccharide building block. If you look down here at my bullets, it's the most common monosaccharide building block. It's something we see all the time. It's in table sugar. It's in something called amylose, which is polysaccharide that we'll talk about, cellulose, glycogen, and more. So we see it in a lot of different places. So looking at this, we have to fill in, I have just lines here, but we need to fill in which direction each of the oxygens go. So which of the alcohols go. So we have an alcohol on the right, and then on the left, and then on the right, and then on the right again. So this is the most common enantiomer of glucose, just so you guys know. And then I'm going to switch colors to put these hydrogens in so that it's very obvious which side is which. So questions on the side, is this D or L isomer of glucose? So how do we do that? We go down to the chiral carbon furthest away from our carbonyl. So let's do purple. Chiral carbon furthest away, and we're going to put a box around where the alcohol is. It is on the right side, so it's going to be the D enantiomer of glucose. Just as a heads up, the D enantiomer in general is going to be the most common natural enantiomer of sugars. So how do we classify glucose? So this is like our keto, aldo, and then our number. So we had, let's do another color again, why not? So first off, we have on the top, we show that we have an aldehyde. So we have aldo. And then let's number our carbons. So let's do 1, 2, 3, 4, 5, 6 carbons. So we have hex. And then our last portion is just showing that it's a sugar ose. So it's an aldohexose for glucose. And then it says draw the other enantiomer of glucose. So the other enantiomer, we're going to do the mirror image. So we're going to have OH on the left this time, right, left, left. And then let's fill in our hydrogens opposite to those. You'll notice for the most common sugars, there's an oxygen, or the hydroxide is going to be on either side. So one water for each carbon is pretty much how it's split up. So this is going to be now the L orientation of glucose, because we have this on the left side. It was not a very good box. There we go. Okay, so this is glucose. Let's look at galactose now. We're going to look at the most common enantiomer first. What colors did we do up here? Oxygens in red. So for galactose, we have right, left, left, right. Let's fill in our hydrogens on the other side. So this is, again, the most common enantiomer. Let's see if it's D or L. We're going to look at the bottom most chiral carbon, so the one furthest away from the carbonyl. And again, it is on the right. So we have D. Galactose is for this particular enantiomer. What is the stereochemical relationship between galactose and glucose? So now we're going to compare this the first box from glucose to the first box in galactose. So looking at the same enantiomer, what is the difference? Well, the difference is carbon number 4, right? So carbon number 4 flips. We had left, right, left, left. Now we have left, right, right, left. So the only difference is that one particular stereo center, or one particular carbon chiral center swapped. So the relationship between glucose and galactose is then diastereomers. Reminder that enantiomers are when everything flips, it's a mirror image. Diastereomers is where only part of it flips. So one or two, not all of the chiral centers, but some of them switch. Structurally, where is galactose different from glucose? We just talked about that. So well, let's number our carbons. 1, 2, 3, 4, 5, 6. So where it is structurally different is the stereoisomer at carbon number 4. So galactose, at least where it's seen in real life a little bit, its most common form is part of lactose. Lactose is a disaccharide. And then additionally, in cellular membranes, galactose is used. Accumulation of the sugar also leads to cataracts, mental retardation, and cirrhosis. So mannose is an aldohexose, which differs from glucose only in stereochemistry at carbon 2. So now let's figure out and use this problem to figure out what the Fisher projection of D-mannose is. So we're going to do the same backbone because we have an aldohexose. So let's draw our backbone for an aldohexose. I'm just going to do black for the backbone. We have our aldehyde. I like to just draw a line. 1, 2, 3, 4, 5, 6 carbons, CH2OH at the end, as always. 2, 3, 4, 5, 6. Okay, so let's go ahead and just copy exactly what galactose is. So we had right, left, left, right for our hydroxides. Right, left, left, right. Draw in our hydrogens. So this is galactose. And the problem says that the only difference, oh man, it's different from glucose, not galactose. What am I doing? So let's change carbon number 4 back over to the right side. My bad. Okay, so we have glucose here. The only change to get to mannose is that it changes its stereochemistry at carbon 2. So how to get to that, all I'm going to do is swap the places of the hydrogen and the oxygen. So now I have D-mannose because I still know I have the correct enantiomer. The bottom carbon is has the alcohol on the right side. And I switched carbon number 2 to the opposite enantiomer or opposite stereochemistry at carbon number 2. So this is now the structure of D-mannose. And then our last common sugar that we're going to be talking about is fructose. So how would let's go ahead and draw in where the hydroxides are. So this is going to be our first, we've been talking a lot about aldoses, which are really common. But this is going to be a ketose, right? Because now we have a ketone in there. So for fructose, we're going to have left, right, right for our hydroxides is the overall structure. So let's go ahead and identify or classify what this is. So we have our carbonyl carbon is now a ketone. So we have keto. We have 1, 2, 3, 4, 5, 6 carbons still, hexose, to show that it's a sugar. So how do glucose and fructose differ? So looking back at glucose at the very beginning, the main difference is that carbonyl carbon, right? So back up in glucose, the very bottom, so let's draw just a line across, from carbon 3 down, for glucose and fructose looks exactly the same. We have left, right, right. However, so let's just verify. We have left, right, right on the bottom half here. So really the top is what's different. You have your carbonyl carbon in a different place. So how do glucose and fructose differ? Well, they're actually structural isomers of each other, or constitutional isomers. Okay, so those are the most common of our sugars or monosaccharides and their Fisher projections. So make sure you keep these as a reference, because we'll be referencing the, or even memorize them if you really like to. I don't like memorizing them, but memorize them or have this handy so that you can reference the overall structure for each of these sugars.